All right, so today we're going to be taking a look at solving exponential equations. All right, so why do we need to solve exponential equations? Um, for example, we looked at this example in the past. All right, Claire invests 5,000 in an account that pays 6.25% interest per year and compounds annually. Okay, uh, how much will she have after 4 years? So we can sit here and set this up. So the amount, okay, A of t is going to be her initial investment times 1 plus r. So 1.0625, right, raised to the fourth power. Right? That's when t is 4. Right? Which is what we want. So if we do this, what is the answer? So we go over to our calculator. Right? We type that in. Our answer is $6,372.15. Right? So now how many years will it take Clara to have 9,000? So obviously it's going to take more than 4 years. Okay, but if we wanted to solve this, right, we want to know when does 5,000 times 1.0625 raised to the t, when does that equal $9,167.68? So obviously we want to be able to isolate t, all right? But if we can't do that, then what do we need to do? We could just kind of make a table of values. So we could go back to Desmos, okay, and plug in t here. Oops, go lowercase t. And we have this function here that we don't see on our graph because it's too far zoomed out or zoomed in. All right, so we want to see a table of values here. And so you could see, right, at 0, it's 5,000. So you just keep making your table of values. We know at 4 what it was. So we got to go bigger than 4. So 5 is that, 6, 7, 8, 9, 10. And I believe that's what we were looking for. 9,167.68. So after 10 years, so we could use Desmos to create a table of values. Okay. And so after 10 years, it'd be $9,167. Now, is that the only way to solve this? No, we know that using Desmos, okay, we could, oops. Yes, erase, I'll type it back in. We can set up an equation, 5,000, 1.0625. And then we could also go, and we want to know when it was $9,167.68. And so what we want to do is we want to zoom out. Okay, until we get 9,000 on the screen. There we go. You can zoom in on that now and see where they cross at. And so it's going to cross when x is 10. So you could graph both of them. We've been doing that all year, solving by graphing. So you could graph the left side of the equation, graph the right side of the equation, and see where they intersect. So this is like when a linear intersects an exponential, all right? And so we can see it graphically as well. But we also want to know, is there a way to do this algebraically? And so is there a way that I can isolate this t by itself? And so we learned that a logarithm is, right, an exponent. So can I rewrite this as a log? And so to do that, right, we would divide, okay, both sides by 5,000. Right, we get 1.0625 raised to the t equals 9,167.68 over 5,000. Oops, forgot the 7. And now I could just rewrite this and use my calculator. So log base 1.0625 of that fraction equals t. And guess what that is? That's 10. You would just type that into your calculator to get that. All right. An open-ended question here. It says, if you were given 5 to the x equals 5 to the y, what do you know about x and y? Well, I know that they are the same. They're equal. And how do I know that? Well, assuming this is a true statement, right? 5 to the x equals 5 to the y. If the base is the same, then the exponents must be the same. All right. And so this is going to be a big thing, is if we can make these bases the same, then we can solve exponentials. If it's an exponential equal an exponential, if we can make the bases the same. All right, so we have some examples here. This is, okay, these are systems of exponentials. So I have an exponential on the left, I have an exponential on the right, which is different than that money example, which was an exponential on the left and a linear on the right. So how can I solve this? Well, there's a couple ways, all right? First way, the easiest way would be to make the bases the same. All right, and so if I can make the bases the same, which in this case I can make both bases 4. 16 is 4 squared, right? And so this is the same as that. These are the same, so all I really care about now is x plus 2 equals 2x. And now I just subtract x from both sides, and you get x equals 2. All right, over here with the 9 and 27, I can make both of these 3, right? So 9 is 3 squared. And so again, I'll kind of show the work here a little bit. So it looks like this, which means I have a power to the power. So when I rewrite it, I'm going to have to multiply exponents. And so I get 3 to the 16 minus 2x. And over here, I get 3 to the 3x minus 9. So my exponents or my bases are the same. So my exponents must be equal. So 16 minus 2x equals 3x minus 9. And then add 2x to both sides. Add 9 to both sides. I get 25 equals 5x. So x equals 5. All right, so strategy 1 here is to get the bases the same if possible. That's the easiest way. All right, if you cannot get the bases the same, okay, and then strategy 2, if I just erase this, would be to log both sides. And so, because as we learned last week, logarithms are the inverses of exponentials. Okay, so when I log both sides, I get log, I'm doing log base 10. Okay, I mean, obviously this one I could do log base 3. It would make it easier, but I'm just going to show you for all purposes, because if we couldn't, okay, do it. So we go log base 10 on both sides, so the common log, okay, and then since a log isn't the exponent, this is the power of a power, this is being multiplied by that exponent. So the 8 minus x could go in front. The x minus 3 can go in front because it's just being multiplied because it's a power of a power. And sorry for my sloppy handwriting, that's a 27. So now log 9 is an actual value. Okay, I mean I could distribute this, so it's 8 log 9 minus x log 9. Oops. Equals, right, x log 27 minus 3 log 27. Get all the x's on one side, right? So add this to both sides, add x log 9 to both sides. Add 3 log 27 to both sides. And so I'm going to get on this side x log 27 plus x log 9. And on this side, 3 log 27 plus 8 log 9. And so factor out the x, so x equals, or x times log 27 plus log 9 equals this, and then, sorry for the sloppy handwriting. Okay, and so I could just divide both sides by that. Again, these are values. If I type these in my calculator, I get a decimal, right? So when I divide both sides by log 27 plus log 9, right, I'm going to get x equals 5. So let's just check that out over here on Desmos. So if I go 3 log 27 plus 8 log 9, so 3 log 27 plus 8 log 9. All right, and then we're going to want to divide that, okay, by log 27 plus log 9. And there's my answer, 5. Okay, so obviously what was easier was getting the bases the same, right? But if there's ever a situation where we cannot get the bases the same, then we have to log both sides. Okay, we'll definitely use the calculator. You could have used your calculator up at this point right here and just change log 9 to your decimal, right? Change log 27 to your decimal, and we'll work with decimals there as well. Okay, so these two are for you. Again, I'll do one of these. Again, I would just get the same base. Like this one's already the same base, so you're really just solving 2x equals x minus 1, right, which is really, really easy. So x just equals -1. And over here, you have to change the base. I guess I'm doing both of them. So you can change the base, both bases to 2. This one's already a 2. So this one's 2 cubed. So my new exponent, power to the power, I multiply them. That's just 9x equals x plus 16. Subtract x from both sides. You get 16 equals 8x. Divide by 8, x equals 2. All right, so here we have an exponential equaling a linear. So to me, the easiest way to do this would just to use our ability to rewrite logarithms. All right, so when we rewrite this exponential equation as a logarithmic equation, the x is automatically going to be by itself. Okay, and so what I mean by that is again, it's log base 5 of 60 equals x. Okay, and so we just have to type that into the calculator to get our answer. Okay, log base 5 of 60. That's what we're doing right. Yeah. So that was 2 point, and again, you got to pay attention to what it asks you to round to. All right, so 2.54 4 if it's to the nearest thousandths. And so there we go. And again, right, if your calculator does not do the base, right, we would have rewritten this as log 60 over log 5 and gotten the same answer. Okay, so if you were asked, right, for the exact answer, then you could leave it log base 560. You could rewrite it using the change of base formula. And there's times where if it's multiple choice, this is probably going to be the answer that you see. And let me show you why. Because the mathematical way of doing this, we're not just rewriting, it's algebraic. So you do something to both sides is you would log both sides. Okay, and so you log the left side, you log the right side. And again, remember, a log is an exponent. So when you have a log and this thing's being raised to another one, it's just the power property. So this x, these are equivalent statements. X times log of 5 equals that. Okay, and so that's just a property, okay, that says, right, log base b of x to the n is going to be the same as n times log base b of x. Okay, this property right here allows us to do this. Okay. So now erase that property off the screen. Now, how do I solve for x? I just, obviously it's x times log 5, so I just divide both sides by log 5, and I get log 60 over log 5. All right, which we already know to be 2.544. So you can leave your answer like this, log 60 over log 5. Or if it says round to the nearest thousandths, you'll round to the nearest thousandths. All right, so let's solve these three and let's look for similarities and differences. So again, if I just rewrite, let's use the rewriting thing here. So here, like the x minus 1 is the exponent, so it's ready for me to rewrite. Okay, it's an exponential where that power is by itself, right? So I could rewrite this as log, oops, let me make my pen a little bit thinner. So it's log base 4 of 5 equals x minus 1. And now you have to add the 1. So my answer, log base 4 of 5 plus 1 equals x. At this point, we would just use our calculator, okay, to change that to a decimal if we needed to. This is the exact answer, okay, but we could change that to a decimal. Now for this one, okay, I need to, before I can log it, I can't log it because there's this minus 1 here, so I need to add 1 first. You notice the difference, right? So now it's 4 to the x equals 6. And now I can rewrite it as log base 4 of 6 equals x. All right, so some similarities, same base, okay? But here it was already isolated. The exponential part was already isolated, and this one it wasn't, okay? Now on this one, okay, got a couple extra things going on here, right? Okay, so before I can log it, I have to get this 4 to the x by itself. So I'm going to get rid of the minus 1. So just like the last problem, I'm going to add 1. Now I have 2 times 4 to the x equals 6. And now, again, just the power is not by itself. It's being multiplied by 2. So I want to get rid of this 2. So I'm going to divide both sides by 2. Now I get 4 to the x equals 3. And now at this point, okay, I can rewrite it. So log base 4 of 3 equals x. All right, so a lot of similarities. Okay, they all end up with base 4 because they all have some form of 4 to the x in it. All right, but before you could log, right, you have to get that 4 to the x by itself, or that 4 to any power by itself, okay, before you log. All right, and if there's something else in the exponent, then your last step would be to get rid of that. If it's not in the exponent, you got to get rid of it first. All right, so you're going to try these right here. I'll let you guys do that on your own. All right, so now we got this one. Again, we have 1/9, 27. Can I make these bases the same? And the answer is yes. I can make 1/9 3 to the negative. Oops, let me adjust my pen here. Right, that's 3 to the negative second. 27 is 3 cubed. So again, this would be the easiest way to get the bases the same. So I get uh, negative 2x plus 8 equals 6x plus 3. Again, I'm just multiplying the exponents together, dropping the bases because the bases are the same. And so I can solve. I subtract 3, I get 5. Add 2, I get 8x. So x equals 5/8. All right. So again, get the same base. So in 1/9 is 3 to the negative second. Multiply those together, power to the power, to get negative 2x plus 8. All right, over here, 27 is 3 cubed. Multiply power to the power, 6x plus 3. And now we're just isolating the x. Okay, so here, what do we notice, right? We notice it's an e. Okay, so we learned last week that base e is just the natural log. So I want to get the base by itself, so I got to get rid of the 2. Okay, so the first thing I'm going to do is divide by 2. So I divide both sides by 2. I get e to the 4x equals 3. And now when I rewrite this, right, it ends up being log base e, right? So instead of writing log base e, I just write natural log of 3 equals 4x, and then I divide by 4. And so x equals natural log of 3 over 4. And that's my answer. Again, you could type that into your calculator, get a decimal, or you can leave the exact value here. Just reading the directions. If it doesn't say to round, I would leave it like this. All right, and then that's for you to do. I'm very comfortable with the content. All right, hope you enjoyed that. I know I enjoyed making it.